Very good afternoon, all students. Now we are towards the winding up of this semester, and we have completed almost all important topics related to data structures. I'm sure all of you have improved your coding. We are left with few miscellaneous discussions, which are relatively of higher understanding level, better complexity level. So we are going to touch upon those. And one such topic we are going to touch today is related to sparse matrix discussions, but via linked list. So we have already done sparse matrix related operations using array. Now we are going to see it via linked list. So if you just recall, we had a sparse matrix where few non-zero values existed in the total big size matrices, and we stored them in a different manner. And what we stored was that we represented them as a 2D array consisting of three different entries, where my row number 0 consisted of total number of rows, total number of columns, and total number of non-zero values. And from entry 1 onward, each, if this value is, let's say, 8, then there will be 8 more total entries. And what we had here was correspondingly first non-zero value. Let's say it is 0, 2, and some value 3, or maybe let's say it is 0, 0, 2. Let's take a value which is discussed in the book also. Then similarly, I have, let's say, 1, 0 as a 4. Then we had 1 and 3 as correspondingly 3, and so on. So we have all these values in this particular format. So this was array-based storage. Effectively, either using structure or 2D array, whatever you, either array of struct it could be. We have discussed both earlier, or 2D array. But of course, this can be done via linked list also. Now, when we talk of having this to be implemented using linked list, one simplest case can be that first simple or first representation, which is relatively easy and simple, can be that we will just consider it as first node, which is your 0th node, as your initial node. Let's say you have sparse matrix, sparse 1 or list 1, whatever you say. I'm not sure whether this is okay. Let me just have, somewhat better. I think the focus is better now. So I just adjusted the focus. So sparse 1, for example, if I say I have a matrix of some order rows, some order columns, and some non-zero values, and then I say for each value, I will store it as a node into the linked list. So I have a next, then I'll say 1, 0, 4, and so on. So effectively meaning that this whole becoming one node, this becoming another node, and all these individual rows, so effectively are linked. So linked list of row-wise of rows of sparse matrix representation. That can be simplest. Of course, there can be better way also, but I'm talking of this. This will effectively mean that this always will exist, and it is effectively a kind of a header node. So header node presence makes things much more easier. Programming will become easy, and exceptional cases will be easily handled because header node will always exist. So that straight away becomes simplest way. Not only that, the header nodes column, this value, like here I have rows, here I have columns, here I have effectively count of nodes, count of non-zero values, effectively meaning that my total nodes in the list get defined. So my total list length will be obviously 1 plus 8. 1 is your header node. So after header node, there will be exactly 8 nodes. So after header node, I also know how many nodes exist, which normally linked list doesn't know. This all can be advantageous to do different programming and handle things in an easy way. So all that makes things simple. And if you do like this, effectively, I am not supposed to do something more than just to have same programming. So now programming will be simple. For example, if I have to do the programming for a transpose, whatever transpose logic earlier we have written, that same logic will still continue. And the only thing is, instead of when you said I++, we have to follow effectively current arrow next. Whenever I wanted to go to next record, I'll just have this. Similarly, whatever logic I have implemented using fast transpose, that also almost same and still easy, still not an issue, not much change, because all that logic is more or less same. The only thing is we are not going, you are using I++, we have to effectively go via next. So next entry, which is effectively a non-zero entry, whenever you want it to go, effectively you have to go arrow next. That's it, not a big change. So if you remember now, more or less these operations we have already done, and whatever time complexity they had, the same complexity will be still possible via this algorithm also, because no change. Why no change? In both of these earlier also, using array also, effectively we always used the entries in a sequential manner only. We never bypassed any entry. All values were always processed in a sequential manner only. Hence, in a linked list, it is straight away possible. And linked list has the only restriction that a sequential access was only permitted, and this works. But using array also, we never jumped to any random entry into this. We never had a direct or random access to any random entry or any random non-zero value. We all went sequentially, and hence all things will become simple. Hence, no special advantage of array was taken, and hence linked list storage will work as it is. Because the array has a special advantage of a direct access, but that was not explicitly used for any operation. Not only that, even for your addition logic, addition of two sparse matrices, again you can have things in the similar manner. No much change needed. Almost similar logic and similar programming will be needed. Effectively, it will become even easier because header node will be present. And for example, if I say I have the header node available to me for doing some processing, I will say, let's assume I had some matrix which had some size given here. Let's say matrix is of order of 5 into 6, and total non-zero entries are, let's say, 8 into your SP1. So this is your first list. Similarly, you have your SP2. Here, let's say we had some entry 0, 0, 2. Then we had, let's say, 0, 4, 3. Then we had, and some more entries. This side, let's say we had entry 0, 2, -3, say 0, 4, -4, and so on. And so if I have to just do the addition will first of all mean, of course, I will check this and this order versus this and this order. If order okay, then only insertion and the addition allowed, otherwise obviously not. So addition allowed and header node guaranteedly exist. So I could say, let's say I have list1 or temp1 variable here, and I can have temp2 variable here. And then I can easily say while temp1 not equal to null, temp1 not equal to null, let me write clearly. So I'll say while temp1 not equal to null and temp2 not equal to null, we will keep on doing this process. And obviously now we could compare if row number same, if some row number is, if row number 1, if let's say temp1 arrow row is less than temp2 arrow row, so that obviously means the same value is directly copyable. Temp1's value will be copied into output, into say SP3 list, and temp1 incremented, shifted. Shifting will mean effectively temp1 becoming temp1 arrow next. Similarly, if the rows were equal, if this row was greater, then temp2 was going to be used. Else, meaning that row number is equal, then same process for column number. And you can proceed like this. So effectively out of these, first time I'll find this node will be copied as it is and my temp1 will shift. Next time temp1 versus temp2 comparison. Now this node will be copied as it is and temp2 will shift. Now both have same row number and column number. They will be added together and new coefficient or new value will be generated and copied and both will shift. And shifting is basically because the ordering is guaranteed. All values are stored in increasing order of row number and for same row number in increasing order of column number. So same logic, just we have to accordingly adjust for pointers using next for going to next increment. For going to next element, that's it. And once we come out of the total loop, say while loop is over, after that remaining elements to be as it is copied. And remaining elements could be existing into your list 1, that is SP1 or SP2. They are to be copied as it is. So same logic we have earlier done without much of a change. Hence, all this process becomes simple and we can easily use this programming. So linked list, this simple representation, so what I said was a first linked list representation. In the book, we have a better, other more useful or second representation also that we will talk just after a few minutes. And that will have some much more advantages also. But before going to that, we will understand this and correspondingly time complexity. Then we will come to second representation, and that second representation is given in book also. But for the first representation, let's understand the time complexity issues also. Because earlier, while talking of the sparse matrix, we didn't see why we went from transpose to fast transpose. So whatever logic for transpose we made, then we went to say that we are going to make it as a fast transpose. And now we will see how we were improving the time complexity actually. When we said fast, it actually meant improving the time complexity. And how that happened, let's understand now. So I'll just show you the code which we have written earlier for the sparse matrix. If you just remember, sparse matrix, a transpose, a normal transpose, not fast transpose, effectively had two nesting loops, nested loops, one loop for number of old column number of times, and then non-zero entries were n. So effectively, there was a nesting of a loop. For every I, this j1 to n was repeated, taking old column number 0, which now becomes row number 0, and we tried to find all entries which had new row number 0 and copied them. Then we changed new row number to become 1, that is I to become 1, old column number I becoming 1, and finding all entries which existed with old column number 1, they will become now new row number 1, hence we copied all this. So this was the logic which we written. Corresponding to this logic, if you see, what we have done was, we had in the transpose two loops, two nested loops. And corresponding to two nested loops, we had I loop 0 to old columns minus 1. And then we had j equal to 1 to non-zero. I'll use this. Effectively, old columns times, so for every I, we had the loop, second loop j being used 1 to n always. This effectively means, in terms of a step count, effectively I will have approximately column number times multiplied by n times, approximately, plus minus something, but that effectively means in terms of a big O complexity, it will be called as O of columns into n. Old columns, that will become new row number, and because of nesting actually meant that they will be multiplied, and because for every I, all j's will be used. So this was your time complexity. Earlier, we didn't mention big O time complexity, but now you can appreciate what is it. Similarly, for the fast transpose, we say in the fast transpose, we were able to improve the time complexity. How? Let's have the look on the code, which we have discussed at that point of time. So at this point of time, we had written your fast transpose like this. So here I had initially old column number of times, new row terms array to be initialized. So this loop executes column number of times. This loop executes n or n plus 1 number of times. N or n plus 1 more or less now same in terms of big O time complexity. So you could see this was 1. Then we had the starting index computed corresponding to all columns. So that again executed column number of times approximately. And then all n values being decided to go into the transpose matrix at the corresponding index. And this was the corresponding logic we have written. So effectively here we have 4 loops, but no nested loop. All loops are independent. One loop completed, second loop started, third loop started, fourth loop started. So this was what logic we have written earlier. Going to the discussions now. So let me just have the discussion continue, and let me have this side. So now if you see here, we had 4 loops, but I claim them as parallel loops. So parallel loops effectively mean My first loop executed approximately column number of times. My second loop executed approximately n or n plus 1 number of times. My third loop executed again column number of times to calculate the starting position. And fourth loop, where corresponding entries were shifted, again executed n or n plus 1 times. Total steps, if I count, approximately will become number of times the first loop executed, but after that there is no nesting. So second loop after that will have these many steps extra. N or 2n, if within one statement there are two statements, so it is 2n, but we say in terms of time, big O complexity, it will remain more or less same. Then again, third loop, within the third loop, maybe I had three statements. So you could say three statements will mean that three statements will mean I will have approximately three columns or anything, but I'll say three doesn't matter. Here also, if it was two statements, I'll say two doesn't matter. So effectively number of columns times. And this statement might have, let's say, four statements or five statements. So it could internally mean 4n steps, but I'll say four doesn't matter much. Effectively, in terms of a big O complexity, it becomes a columns plus n plus columns plus n. Indirectly meaning it becomes order of 2 into columns. If I mathematically calculate the above solution, here both are being repeated, but again 2 doesn't matter. So primarily it becomes order of a columns plus n. So now you can see that both time complexities changed. So this is faster because this is guaranteedly less than multiplication values. If I say columns were 10,000, if n was, let's say, 200, you can easily say 10,000 plus 200 will be much lesser than 10,000 into 200. Even if this executed, let's say, 5 times in total, still it will be 5 into 10,000 plus 200, and this side is going to be much, much bigger. Say five different statements, let's say, in all loops. So in that case, it could mean 5 times, and still it will be much better choice. So I claim that all this way, it becomes much better choice. Similarly, I can say that for any algo, whichever I'm making, the same logic will be still applicable, and I can still do my same processing for the implementation. Similarly, if I talk of the corresponding discussion correspondingly to sparse matrix addition, again I can say addition logic, what was the time complexity? How much is the time complexity? Can I estimate in terms of a big O notation? So I can easily say I had a while loop with AND condition, and then I had another while loop for copying terms of first list, remaining terms of first list. And similarly, I had another while loop for copying remaining list terms of SP2. And here I had list base. So if I assume my SP1 has, let's say, N1 node and number of non-zero elements, SP2 has N2 as a size. Size means number of non-zero elements. How much is going to be the time complexity? Of course, now you have to think in terms of whether it is N1 into N2 or N1 plus N2 or something like that. Of course, you could say whichever is bigger, but whenever we have such a situation, whenever input is dependent on more than one parameter, we don't assume anyone to be bigger or smaller. We have to make the big O complexity for both being considered in the equivalent manner. So both will be reflected into my time complexity notation. So will this while loop execute N1 into N2 times or not? I say no, because in some cases or in all these cases, it was never that for we had never a situation that for every SP1's node, all nodes of SP2 considered. No. Or all nodes of SP2 traversed and compared, or this. Had this been the situation, then only N1 into N2 will be the situation. We had a situation, they were compared and one of them was used. So obviously you could think N1 plus N2. But I say a better strong logic is needed to understand this, that in above while loop, each node of my list SP1 as well as SP2 will be traversed not more than once. Will be processed, I will say, not a traversed. If it gets used once, and then it will never get again processed or used. So exactly once it will be processed. Processed means when either it got copied or it was copied through addition. So every node will be done once and exactly once. So that effectively means N1 nodes of list 1 will be guaranteedly processed. That is must to be done and they will be processed only once. Similarly, N2 nodes will be guaranteedly processed once and exactly once, and they don't repeat for each other. They could be simultaneously used and one of them or both of them get processed at the same time. Hence, broadly speaking, I can say it becomes order of N1 plus N2. Of course, what do you mean broadly? I'll define mathematically also today, but I can easily say whatever I know is true now. You could say further this will also probably execute N1 times, this will execute N2 times. So you might say that my first while loop that executes, you could say N1 plus N2 times. Then second while, you could say it executes again N1 times. Then third while, you say it executes N2 times. And then you could say N1 plus N2 plus N1 plus N2. Still it becomes order of N1 plus N2. Well, I'll say this statement is partially correct in the sense that this is okay, but addition of this is actually incorrect. Why? We need to understand. First thing, there is no guarantee that this will execute exactly N1 times, but you could say, fine, worst case, it could execute N1 times. Similarly, in worst case, it executes N2 times. Yes, in worst case, it executes N1 and 10 times. But if so, then above loop will not execute N1 plus N2 times. So that is the challenge. If second while executes, let's say, N1 times or N1 minus 1 times, effectively will mean first while loop will execute only N2 times mainly. First while will execute probably one time, or if N2 was completely exhausted, only first one node of first list was only processed in the first while. That's why second while executed N1 minus 1 times. So probably what you understand now is that when I said each node gets exactly once processed, this exactly once will happen throughout totaling loop 1, first while and second while. For N1. And similarly, N2 times a second will mean effectively totaling first while and third while. Because whatever remaining elements are in a list, they will be processed via second and third while. And if they were already exhausted, this loop will execute effectively 0 times, means only one checking will be done, and that is it. So I say this addition was incorrect. This is always going to be big O of n plus 1 plus n2. where this is total for all three while loops, and no additional plus needed, although that will not get reflected into the time complexity notation, but still it will be incorrect to add them and then ignore the multiplying or the additional values of the constants, etc. Because this itself considers all this. Then why I say now this is again going to be, so in some logics, just you don't see the parallel loops never always mean that add them. No. So this might not be always true. Parallel loops normally will add their steps, but here in such situations, you have to find out the logic will tell that how many exactly times the main statements will execute. And through that, your time complexity will be found out, or step count will be found out. Knowing all this, so now I say, can we mathematically define big O complexity and understand it in a more meaningful manner, so that you don't get confused in going in such finer details? So I'll say, let me define it mathematically. So let's say, assume that step count approximately or exactly step count of some algo is found and denoted as f of n. For example, f of n could be, let's say, 2n square plus 5n plus 6, or it could be n square plus 7n plus 18, or it could be 3n plus 15, like this. Whatever number of steps, exact count, having all these constants also. Then I say, effectively, big O complexity tries to find the most dominating term, and that is the notation asymptotic or approximation, most dominating term to be found. And mathematically, how we define? I say Fn is said to be having a big O complexity of some notation Gn if and only if there exist some positive constants. Two positive constants will exist, C and N naught, such that my notation will always have Fn to be always less than or equal to C into G of n for all n greater than equal to n naught. So this is my mathematically definition for big O notation. What does it mean? Effectively, it says that if you are able to find, let's say Fn is something approximately n square plus 7n plus 18. So I could say this can be represented to be something less than, let's say, 2 into n square for all n, let's say, greater than equal to some value. I can say mathematically always possible. If such definition is always possible to find some constant C which can be replaced here, some n, let's say, for example, if I say n is a 5, so this will become 5 into 5, 25 plus 35, 60 plus 18. This becomes a 78. 5 into 5, 50. So no, 5 might be incorrect. Maybe I say, for example, n equal to 8. 8 into 8, 64. So if I have 64 plus 8, 7, 56 plus 18. So this value will become, let's say, if it is guaranteed to be less than 128, which had probably 65 plus 1. So approximately 8 also not satisfying. Maybe for 9, I will get satisfied. So for n greater than equal to 9, it is guaranteed that this will be always less than 2n square. So in that case, C equal to 2, n naught equal to 9, And from here onwards, n being 9, 10, 11, and so, biggest value, very big values normally we consider for n. Hence, for all such values, this relation will hold. If so, then I say my time complexity is order of n square. And the basic purpose of all this is to find the most dominating term. Similarly, if you say, for example, I have 2n square plus 5n plus 6, I will be able to say probably this to be less than equal to 3n square for all n greater than some value. If so, again I say my time complexity is order of n square. So the purpose is effectively to find the dominating term. And that's why mathematically we claim this. So I say whether my algorithm has complexity of, let's say, 3n1 plus 5n4 and plus 2n2, I say this is going to be claimed to be order of n1 plus n2. And plus minus something, because some constant c will be possible, because I can say 3n1 plus 2n2 can be mathematically written to be less than equal to some constant n1 plus n2 for all n1 and 2 to be greater than something. Maybe I say I write here c to be 3 or 4, then I can guaranteedly claim this will be okay. So I say approximately, I can always claim this to be like this. Hence, constants with multiplication of the input sizes plus minus something doesn't matter, and dominating term matters. Not only that, if n square is the dominating term, then all these for big values of n will be much smaller than the square of n. Hence, these values will not be considered much, and they will be effectively ignored when the dominating term gets counted. So this is how my big O complexity is defined. Having said that, now I can say, knowing this complexity notation, you can probably revise your selection sort time complexity. If you remember selection sort, I'll just show you the code and then you will be able to recall that. So here is my selection sort coding. Now in the selection sort, if you remember, this was the logic. So I had a loop, and within the loop, effectively, I had j equal to I plus 1 to n, min index was found. So in this case, this was the logic. Now, what effectively we did in that case? So what we have done here was, we had an outer loop, which could execute, let's say, from 1 to n minus 1, and you could say I loop. And then inside this, I had a j loop, which I said I plus 1 to n. When I is 1, this loop, so I equal to 1, this loop executes 2 to n, that is n minus 1 times. I equal to 2, this loop will execute 3 to n times, that is n minus 2 times. I equal to 3, it will execute n minus 3 times. And when I becomes n minus 1, effectively it will execute 1 time, n minus 1, that will be 1. Total steps. You have to effectively find inside this how many total steps were there. So the total steps are 1 plus 2 plus 3 up to n minus 1. Some could say, no, it will be 2 plus 3 plus 4 up to n. Doesn't matter, because this series summation effectively becomes n into n minus 1 by 2. That means n square minus 2n, or n square minus n, and like that by 2. So I say effectively this becomes total value. But in terms of a time complexity, it will be called as order of n scale. So whether its series was a 2 plus 3 plus up to n, the summation could be n into n plus 1 by 2 minus 1. That will mean n square plus n by 2 minus 1. Still, it will have time complexity of order of n scale. And I say this complexity is always the same for any data. Whether you had a sorted list, you had unsorted list, you had a random list. Every time the steps are same, because your first time you will say find by comparing all values the minimum index. Even if the list was sorted, you will go up to the last element, confirm that your min index is properly found. So every time these steps are always going to happen. Hence, my time complexity is order of n square always for best case, for average case, or for worst case. But for insertion sort, it might not be true. It will be different for best case and different for worst case. Why? We will have a quick look in that discussion. So I'll say, let's go back to the insertion sort code. So I'm ready with that code also. And here is the code. So in insertion sort, we said we will try to insert the new element into the sorted list. So up to this, the list was sorted. Up to J list is sorted. And array I being inserted into the sorted list by shifting. So how many times this while loop will execute is not always the same. Depending when this condition becomes false, I might come off the loop. So remembering this code now, if I see and go further to the analysis discussion, just have a look. I wanted initially to say, let's say array 1 to be inserted into empty list. Empty list. Say one step will take. Then array 2 to be inserted into sorted list. Now sorted list means, let's say I have value 25 and now you are trying to insert, let's say 30. So 30 will mean no shifting needed, but if this value is a 20, shifting needed. So the steps will differ. For example, if I say array 10 to be inserted, that will mean I have a list, sorted list, let's say 2, 3, 5, 7, 9, 11, 1, 2, 3, 3, 6, 13, 17, 21, 20. This sorted list exists. And here, if I have, let's say 25 to be inserted. Now, this list has 9 sorted elements. 25 insertion, no shifting needed. While loop will immediately terminate. No shifting of elements or swap place to be created. And immediately while loop executes once only. First condition itself will make the while loop false and I will be able to insert. So effectively, I say if I had a sorted list, every time my while loop will have minimum steps. So best case means minimum steps for wherever possible. This becomes best case. So in best case, for first element, one step only needed. Say array 1 to be inserted in an empty list, only one step. Array 2 to be inserted into already sorted list, but because this element will always come at the last position only, so one step only. No shifting will be needed, no while loop will repeat. Third to be again in one step only. Every time, no shifting needed and all elements getting one step only. 1 or 2 or 3 fixed number of steps, no n-based steps. So effectively, if you sum all this, it becomes n. Even if you say, let's say it needed total 3 statements, means 3 steps. So each requires 3 steps, each require 3 steps. summation will mean it becomes a 3n, and a 3n also means order of n. So best case time complexity in case of an insertion sort is going to be order of n. But worst case, let's say reverse sorted list. If I had reverse sorted list for my insertion sort, now every time the while loop has to execute maximum number of times. For example, array 10 to be inserted. Let's say I have 2, 3, 5, 7, 9, 11, 13, 17, 20. So I'm talking of some element array n to be inserted, and n minus 1 elements are already in the list. Let's say this value was 1. Now, if this value is 1, n minus 1 times or n times effectively my while loop will execute. So when my first element was array 1 was being inserted, let's say it takes 1 step, but when array 2 comes, it will take 2 steps because all elements need to be shifted. 2 steps or 3 steps, whatever you say. Third element, all previous 2 elements need shifting. Fourth element, all 4 elements need shifting. Some n minus 1th element coming, all n minus 1 steps needed to shift. Nth element coming, all n steps or n minus 1 steps, whatever you say needed. So whether you say this, effectively, if you sum up, this becomes order of n square. So in worst case, insertion sort is going to be order of n square. But in best case, it is going to be order of n. Hence, there are some algos which depend on data characteristics. Selection sort was not, but insertion sort is. On the other hand, it doesn't mean that sorted list is always the best case. Don't assume that. That assumption will be false in case of quicksort. Like all of you have studied quicksort, we have not done the analysis, but I say in quicksort, if the list is sorted, whether reverse sorted or any order, or ascending order or descending order, in both cases, this becomes the worst case. And in this case, the time complexity comes out to be order of n scale. On the other hand, best case time complexity in quicksort will be order of n log n. And best case happens when list gets divided or when pivot reaches to middle always. Whenever we can ensure that pivot reaches to the middle position always for every recursive call, in that case only the best case will happen and a time complexity will be coming n log n, because every time size will reduce from n to n by 2, n by 2 to n by 4, n by 4 to n by 8, and then hence accordingly log n will step in into the solution. So that will become the best case. So it doesn't mean that a sorted list always means best case. No. In this case, a sorted meant worst case. Why sorted was worst? Because pivot was reaching to last or one extreme position. Either leftmost or rightmost in both cases. If sorted, if list was sorted, either it will reach to the first position or it will reach to the last position, depending whether it was ascending order sorted already, reverse sorted. So if my data or input was a sorted list, my pivot reached to extreme positions, and that will mean worst case, because every time one list will be empty. If I have, let's say, pivot, if pivot reaches here, this list will have n minus 1 elements. This side will be empty list. and my recursion will work only for this when every time size reducing by 1 only, not getting half, half, half. Hence, this becomes worst case. So you have to remember that the worst and best case are characteristics specific. And in case of a merge sort, if you see no characteristics were changing any behavior, so that algorithm always have order of n log n in best case also, or in worst case also. That obviously means in average case also. So merge sort was in this form. Of course, now you, based on our understanding of time complexity, you can revise and have this more clarity by solving. Recursive solutions, of course, we have not discussed for finding time complexity, how to solve recursive problems to find big O time complexity. So using master theorem and some more formulas, you will study next semester and solve that. But going towards the final discussions for today, we said a better representation for linked list better representation for sparse matrix. So that is going to be last discussion for today. And I'm sure you can apply that and read in more detail from the book. So what does it say? It says that we will not have just linked list for row wise, which we have already done just now. It says we will have linked list for column wise also. Effectively meaning that what we are going to link now is we are going to have my linked list for row wise elements of the same row. Earlier I had just a linked list of all non-zero elements linked together without anything special. But now I'll say my all elements of row wise will be also linked. My column wise elements of the same column will also be linked. And this is how my total algorithm will be implemented. Of course, this is going to be relatively more complex than my normal representation, but obviously it will have more advantages also. And it will make things probably much more simpler and easier for some logic developments. For example, if I say I have a matrix 2, 0, 0, 0, I have a matrix for second matrix with 4, 0, 0, let's say 3. I'm taking the example of the book itself so that you can recall when you read from the book. 8, 0, 0, 1, 0, 0, 6, 0. So this is a matrix. This is row number 0, 1, 2, 3, 4. Row number 4. This side I have column number 0 and column number 3. So this is a matrix of 4 into 3 matrix. Had this been stored into array representation, the things could have been 4, 3, and non-zero values 1, 2, 3, 4, 5, 6. And then we could have 0, 0, 2. Then we could have 1, 0, 4, 1, 3, 3, 3, 0, 8, 3, 3, 1, and 4, 2, 6. This could have been the equivalent storage in the array based. But if I say now linked list based, and that also linked list in this form will have a different concept. What it is going to have is now, I will say, first of all, my 4, 3, 6 will be one header node. Now this will have many headers further. Header for row 0. Similarly, I call this as, let's say, H0. Similarly, header for row 1, header for row 2, and header for row 3, header for row 4. So 4 header nodes will be there, where header nodes will effectively tell that this is a linked list corresponding to row 0. So header node 0, effectively this I show here. I'll say header 0 effectively will mean this will be having all entries corresponding to row 0. Row 0 has only one value, so it will have this node 0, 0, 2 and maybe null. And if you make circular list, which in the book is explained as a circular, then this will point to the same header node. So I have here next pointer to go to the next element into the row list. Not only that, I say each of them will have a down pointer also. Similarly, I'll say first of all, for the header 1, reproduced here. This one is reproduced here. And H1 will mean corresponding to row 1. So row 1 has entries 1, 0, 4. And then I have 1, 3, 3. 1, 3, 3. And I have shown intentionally so that in between, if there were some more entries, that will be somewhat relevant. So, and then it is either null or circular as per implementation. So in the book, it is in the circular, so we can use it in the circular manner. Similarly for H2, similarly for H3. But not only that, I say they are connected with column number based also. Column number based linking also established using downlink. Downlink means each of this node has a downlink also. For column number 0, there is another entry and this is linked. This also can have, this was with the next pointer linked to this side, but with the down pointer, it is linked with the next element for column number 0. Column number 0 has another entry 308. So with H3, that 308 was going to come here, 308, and this will be linked with this. H2, there was no entry for this. So this list is null or circular as per requirement. H3 had 2 entries. So 308 and 331. So correspondingly, these 2 entries, and this side, because corresponding to this node, it has the same column number. This link is also there. So you could say I have a downward link also. Making it more clear, I'll show it in form of the node structure now. So my header node could be as I want, whatever properties, but my non-zero entry node where I'm storing the values is effectively having your row number, your column number, your value. These 3 fields are obvious. Along with this, you could say I can symbolically show them to have next pointer and down pointer. Next going to next entry in the same row. And this going to same columns next entry. And using this Now your transpose, etc., becomes much more easier because column wise you need not count or find. Column wise also linking existing, and that column wise linking will be useful because they are going to become the rows now, and this will make things easier and faster. So your coding can become faster for transpose if you have this via this representation. So this is the advantage of all these discussions, and of course relatively much more complex logic, but just to show you in the book what is given, and my screen will be visible here when I show you via this. So you can see in the book the same example which I have just shown you or discussed is given here. This is the matrix which I have shown, and here is the header node, overall header. Then this is header for row number 0. This is header for row number 1, header for row number 2, header for row number 3, header for row number 4. The same header entry is equivalently shown here, where this has only one non-zero entry, header 1 has two non-zero entry, header 3 has two non-zero entry, header 4 has one non-zero entry. But they are downwise also linked in the sense that I could go to the same columns entry, this 0, 0, 0, this 3, 3. So this header node is row-wise, and internally they are downward also linked. So we have a right link and we have a down link. And for other non-zero entries, we had row, column, and value. Header node could be having anything, or it could be anything here, doesn't matter much. So I think with this, I will wind up, but this is given in the book on page number 180 onwards. So this is given in the book from 178 to 182 or 3. So I think you must read that. So I will say from the book, read the book of Horowitz-Sani and pages 178 to 182 or 3 probably. There are sparse matrix alternate representation using linked list and linked list based efficient representation for faster column based searching. So you must read this also, and you will learn a lot of complex issues also via this. As a homework, or I will say practice problem, you must try transpose, fast transpose, oblique addition of sparse matrices, using the first and simple representation we have used. And so this I say first, and then second I say even more difficult problem or more practice needed for fast transpose, along with that input reading, output display, and addition if you want to try of sparse matrix using books representation, means using downlink also. So with this, I think I will stop my discussion, and I'm sure all of you will find this useful for practicing. Especially good students must have tried to these problems. May not be immediately, but whenever you get time, you should try to solve this. This will give you a lot of confidence. Bye bye. All the best to all of you. Stop.